Okay, we will get started. I'm going to share my screen and we'll start the PowerPoint going. Okay, you guys should be able to see my screen. Can you see a screen that says potential applications of NMR to MCC cure projects? Somebody give me a quick thumbs up or a yes. Or I shared
Yes,
the wrong.
I can. Yes, we can see the slides.
Oh, okay, good. Well, we will start. This is the roadmap of what I'm going to discuss over the next 45, 50 minutes, maybe, depending on any questions you guys might have. So cures that use NMR as a sort of a centerpiece of the cure are primarily suitable for upper level biochemistry or upper level biophysics classes. I think it would be very problematic to try and put them into a lower level class, that uses protein NMR. But in the right course, and we've successfully done it in an upper level biophysics course, and it's been a lot of fun and quite informative. But there are various types of questions that you can use NMR to answer in such a course, from ligand binding to looking at protein dynamics, to looking at protein interactions, and looking at protein conformational changes, or more or less any combination of the above. However, what you need to be able to do this is you need an NMR with a big magnet, because of course you're looking at proteins and you need lots of protein and you need a signal to follow. And I'm just going to use fluorine as a signal to follow because it's one that you can specifically add into a protein or a ligand, and it makes sometimes things a bit easier to interpret. But you can do almost any of the techniques I'm going to talk about with just regular proton or regular carbon proton, or typical 2 and 3D NMR techniques. Okay, and you either need to be somebody that's got already a good understanding of NMR techniques and have used NMR, or you need a collaborator with a good understanding of NMR. And I'm as you'll see, a sometime user of NMR, but without having a good NMR person in the department who's happy to collaborate, it would be hard to do a real cure class that really integrates NMR into the course. So I'm going to pick on fluorine as my example to use, primarily because NMR techniques have caught up with fluorine. Fluorine chemistry has been sort of a bit trendy recently, and that allows the synthesis of various fluorinated molecules. And so F19 NMR represents a compelling option for studying a whole range of biological events and protein structure function events. And this particular review is a really nice review. And what I'm going to do is I'm going to point out a bunch of papers that, if you're really interested in delving into it, these papers will actually be, in my opinion, a really good starting point for thinking about how to develop an NMR-focused cure. So this sort of gives you a brief snapshot of the various things I'm going to illustrate in terms of ways of getting fluorine into the system. Okay, if you want fluorine on the protein, you can use fluorinated modification reagents, and these two are both ones that react with sulfhydryls. And of course, if you want them in specific places, you can introduce a sulfhydryl at a specific place in your protein through site-directed mutagenesis, and then use a fluorinated modification reagent that covalently attaches to the sulfhydryl. So, that's one way to get fluorine into the system. The other is to use a fluorinated ligand, substrate analog or a ligand that binds, and that you can make a fluorinated substrate or fluorinated analog of. And then the third way of doing this is you can actually incorporate fluorinated amino acids into proteins at specific places. And I'll give you some examples of that. And the diagrams here are just sort of some cool diagrams to relate those sorts of things. So, the fluorine local environment can be used for screening ligands or conformation or whatever to drug design. This is a cool paper. And you can use, I think the next slide is a scheme of sort of one of the papers with this paper. And these papers are all freely available. If you have trouble finding them, I can send you a copy of them, or anything that you might be particularly interested in. So, again, you've got, libraries of ligands that you can use, and, fluorinated peptides are often, synthesis. You can synthesize fluorinated peptides and use those as ligands. And you can use them as binders to do a binding assay, and you can use them in competition binding studies with a known ligand. So, if you have a fluorinated ligand, and as you'll see in a moment, one of the problems is sometimes the fluorination changes the properties of the ligands. But if you use them in a competition assay against the normal ligand, then you can still use the fluorine NMR signal to screen. Okay. And here's just an example of a fluorinated ligand where you can map what's around the binding site. And as is typical of most protein-oriented, you need fairly high concentrated, low concentrations of the fluorinated ligand. But this is, a word of warning, and that is this paper discusses quite extensively some of the problems that having fluorinated molecules in the system cause, because fluorine, of course, doesn't behave just the same way as a hydrogen. One thing that's interesting, though, and I think it's referred to in this paper, that turns out a fluorinated fluorine position in an amino acid is actually a really good phosphomimic on that. So, if you have a fluorine, because it's more electronegative, so it mimics phosphate much better than, say, just a regular carboxyl group, which is the way a lot of people mimic phospho, PTMs and things like that. So you can do all the sort of regular 2D type NMR experiments using fluorine, and this paper talks about that. and you can look at the coupling constants in multiple fluorinated compounds and things like that. And this paper goes through a lot of the homonuclear fluorine, and cozy and toxy and nosy type experiments that you can do, heteronuclear experiments. So this is a really useful paper. This is a good paper to look at. And this has also got some good examples in it. This paper's got some good examples in it. Again, they talk about the different sort of, multi-nuclear type experiments. And they show some really nice data where they've looked at, various things using this so-called TDOR correlation spectra, where they use the fluorine. I don't know whether this is a technique that we developed actually many years ago now. Like 1987, that was a long time ago we did this. We didn't do it with malate dehydrogenase, but we did it with a different dehydrogenase. And we've been meaning to do it with malate dehydrogenase. We haven't got around. It's using so-called transfer nuclear overhauser effects. And this lets you map, orientation of molecules and closeness of molecules and things like that. And, you can look at the orientation of a ligand bound or the proximity of a ligand to another ligand. And again, you get typically nice signals and you can measure things that, again, like all of these things, and this particular paper goes through all the math and of doing the transfer nuclear overhouse effects and the rationale behind it. And then this is something that's used fluorine nuclear overhauser effects in mammalian rhodopsin to look at the conformation, whatever. And I find when I'm talking with students, if they really understand overhauser effects, it goes a long way to making sure they understand what the NMR is doing for them. So I usually have a demonstration, a physical demonstration, using bar magnets of what an overhauser effect is. How you have negative and positive overhauser effects, and how it basically depends upon distance and orientation and those sorts of things. So, there are ways you can adapt things to get the students to really get into it. And the other thing that I always do is I give them a problem set with a 2D spectrum and get them to work out all the cross peaks and everything and try and come up with a structure from the spectrum. And it's a relatively small peptide that forms an alpha helix. So, they see what an alpha helix 2D pattern looks like. And then after they've done that, I've actually had them then go and collect 2D spectrum lysozyme, which has a nicely defined 2D spectrum. Never done it with fluorinated anything, but it gets them into understanding what the NMR is all about, which I think is really useful. And this is from the paper we were just looking at about the rhodopsin, and where they put in cysteine labels in various places, and they go through and talk about how they get to the data. So if you're going to teach a class based upon one of these, using the paper, I try to pick papers that I think are really friendly for sort of a class journal club type thing. So this again is another paper about the TDOR type approach. Now, these are cool experiments, and we've done these with a bunch of different proteins. I don't know whether you're familiar with pulse field gradient NMR, but if you've got a machine that's capable of doing pulse field gradients, it's a really great way to look at both protein-protein and protein-ligand type experiments, because in essence, it's a way to determine the diffusion coefficient. And I know a lot of people at MCC are interested in looking at protein-protein interactions in some of these sort of metabolon type complexes. And if you've got pulse field gradient capability, it's a really cool way of getting the diffusion coefficient. And then, you know, you can combine it with doing side-directed mutagenesis, things that disrupt the complex interaction or conditions that disrupt the complex, and introduce, you know, as I said, pulse field gradient NMR. So that's a really cool technique. It's a lot of fun to play with. And the good thing is that the actual collecting the data is relatively straightforward. And the interpretation of the data is relatively straightforward. So, you know, that's a cool approach to use if you're interested in looking at protein-protein interactions. And it can be used with almost any size molecule you like, as long as you've got a signal that you can see. And that again is where the fluorine comes in. If you've got a fluorine, you can put in one protein and not in the other, and then reverse it so that you look at it from both directions. Yeah, you know, it's a cool way of looking at protein-protein interactions. Then the last couple of papers that highlighting here are ones that talk about incorporation of fluorinated aromatic amino acids. So this paper is quite a nice paper. And they look at 3-fluorotyrosine, 4-fluorophenylalanine, 5-fluorotryptophan that they incorporate, and they go through how you do the incorporation and everything. And they've used it to look at, you know, positional regions in the protein and those sorts of things. And then this paper is sort of along the same lines, where they use site-specific incorporation of fluorinated prolines and looking at their impact in neighboring residues. And again, that's quite a nice paper. And of course, you know, prolines have cis-trans properties and things like that, and you can look at those sorts of things. Again, you get, you know, very nice. This is just some of the spectra they get, the 2D spectra they get for looking at that. And then this paper talks about, you know, again, I tried to pick 2 or 3 papers about incorporating fluorinated amino acids, because that's, I think, something that people might find a nice part. You know, if they've got fluorine capability, being able to put a fluorine in a specific position in a protein is really cool. And this again just shows some of the sort of spectra you can get from these sorts of experiments. And the last 2 papers, the last 2 things I'm going to talk about, you know, this paper is about where they, you know, they put fluorinated amino acids in, but they wanted to make sure that they were really in the place they thought they were. So they actually did the crystallography, and of course, fluorine shows up nicely in the crystallography too, which makes all sorts of things with the crystallography. So, you know, if you've got a upper level instrumentation course and you've got access to crystallography and NMR, you know, so you can do a great combination of techniques that sort of relate to one another. And then the final one is, of course, the other way of checking that you've got the, excuse me, talking too much, is to use mass spectrometry. And this is the approach we use in our upper level biophysics. We get the students to do a series of experiments that involve both mass spectrometry, crystallography, and NMR, so they can see how you can piece all of these things together and those sorts of things. So with that, I'm going to stop sharing and see if you guys have any questions. Or have I just put you to sleep? And are you there?
Yeah. So,
Oh, you've got your lab assistant with you too.
yes, this is the big boss. This one makes all the purchases. So I was wondering, could it doesn't seem possible, but could we use this with just like looking at 1D fluorine shifts?
Oh, sure, yeah. I mean, a lot of the binding things, you don't need to do the 2D type things.
Yeah, I mean, I would love to, but I'm at a PUI, and the NMR that we have is a benchtop NMR.
Yeah.
So I was wondering if there was any applications towards that.
Well, I think one of the papers on the binding and competition binding talks about that. But yeah, I mean, if you've got a NMR that can, well, with the fluorine, if you've got a NMR that can measure fluorine, you've got a nice, simple, unique signal, and you can look at its shift and how it changes when it's free in solution versus bound to the protein. And you use a competition type assay. So absolutely. And that's probably the simplest way to introduce, some of the concepts. And probably fairly accessible to most people.
Yeah. Okay. Thank you.
Anything else? Ning, you got anything, or are you?
Yeah, just a very quick question. This is very informative, but just wondering, what about like how affordable is all the reagents?
Well, that's always the question whenever you try and do anything. Is people do these sorts of things. Fluorinated amino acids to biosynthetically incorporate isn't the cheapest experiment you could possibly do. What Roderico was talking about was sort of a cheaper type experiment. It just depends what your budget is, and any time you use any of these sort of high-end techniques, they tend to be more expensive than using simpler sort of benchtop techniques.
Sure, thank you.
The real question is there information that you can get quickly and easily? If and a lot of places teach sort of courses that are instrumentation. And so, if you're teaching a course where they want you to go into NMR, then then you got to do it, sort of thing. But you do, for a lot of these things, need relatively large amounts of protein. They're not the sort of techniques that you can get away with, micrograms of protein. You tend to need lots of milligrams of protein.
That's the benefit of malate dehydrogenase, which is relatively easy to get large quantity.
Oh, yeah. Yeah. I mean, if you've got an expression system that behaves well, it's relatively easy to get fairly high amounts of malate dehydrogenase. So, I mean, most of these are accessible to malate dehydrogenase, to be applied to malate dehydrogenase. But You know, if you've got a synthetic chemist that knows how to make fluorinated compounds, you know, it's a great partnership between two courses where one course makes them and the other course uses them and things like that.
That's a great idea. I will talk to some chemistry professor.
Right, you know, and if there's somebody at NC State that, you know, is into organic synthesis and would like to do a collaborative project, you know, and you know, you've got crystallographers there, and I'm sure you've got mass spectrometers there. You certainly got people that know those techniques.
Yeah, that's a good point.
Yeah. Okay, good. So how much
Awesome,
longer are
thank
you
you.
in Germany for?
For the whole summer, like until July?
Oh, okay. And so then you're teaching a cure in the fall, or
Yes. So I offered the MDH cure in the past spring, like this like the semester, and then I'll be doing it again in the fall semester.
right? Okay, good, good. Well, you know, if you're interested in any of these things and you want to talk more about them, you know, I'm happy to talk or send you literature or whatever. But and same with you, Rodrigo. If you know.
Oh
That
yeah.
So,
would be amazing. Thank you.
okay, well, you guys have a great rest of your day. And you must be ready to stop for the day. You know, kudos to you for showing up at, you know, late at night in Germany. So good job. Okay, well, I'm going to stop recording.